Hello, everybody, and welcome to our power lesson. We are cruising through this unit, so I'm stoked with all the work everyone's doing. Everyone's crushing it. And let's dive in here. So, power is the rate of doing work. It is measured in joules per second, which instead of writing joules per second, we have a new unit that is joules per second, but we call it watts, which is a W. So power is in watts. It's the rate of doing work. So the formula is power is work divided by time. Yeah, not too tricky. P is power, and it is in watts. W is work, and that's in joules. And time, T is time, and that's in seconds. You also know, so we know, oh shoot, hang on. We know P is equal to W over T. And we learned the work energy theorem. Work is the change in energy. So you can kind of meld these together to say power is the change in energy over time as well. So there's a few different interchangeable formulas there, and it just takes a bit of just figuring things out to see how they all work. Let's do a couple of practice problems here. Example 1, Lover's Leap is a 122-meter vertical climb. The record time of 4 minutes and 25 seconds was achieved by Dan Osman. He did this without a rope, which was pretty crazy. There's a video on YouTube if you want to watch it. Also, that record has been broken by now, and there's a video of that happening as well. All right, so he climbed up this 122-meter vertical climb in 4 minutes and 25 seconds. What was his average power output? What was his average power output at this time? So we have a mass. His mass is 65 kilograms. We have the height. The height is 122 meters. We have time. Time is 4 minutes and 25 seconds. This one's a bit of a weird one. We want to convert this to seconds. This chunk is already in seconds, so we just want to convert this one into seconds. So 4 minutes multiplied by, 1 minute is 60 seconds. So basically 4 multiplied by 60 is 240, and we have 25 seconds. So our actual time is 265 seconds. So we'll keep that one over the other ones. So we're looking for power. So power is work over time. We don't really have work. Work we know is force times distance, and we don't really have a force. So what we could do, actually, there's a couple different ways we can think about it. If you wanted, you could think, let's do it this way. Let's do this. Let's do it twice, and I'll show you there's a couple different ways you can think about it. We know power is force times distance. If Dan Osman is climbing this cliff, he is working against gravity. So he is having to apply a force opposite of gravity to get himself up this 122 meters. So the force he is working against is gravity. So we could say, well, his force now will be mass times gravity times the displacement over time. His mass was 65 kilograms. Gravity was 9.81, and the displacement was 122, and he did that over 265 seconds. The other way you can think of it, and this is what's really cool about this unit, is that there are multiple ways to go about this. Work is also the change in energy, so we can say the change in energy. In this case, he's gaining height, so he's changing his potential energy, T. Change in potential energy is P final minus P initial, right? EP final minus EP initial over time. But if he starts on the ground of this cliff, his height will be 0. So he's going to have no potential energy initial. That goes away. So we're looking at EP final over time. And EP final is mgh over t. So mass times gravity times height, 65 kilograms multiplied by 9.81 multiplied by 122 all over 265 seconds. So it ends up coming out to be the same calculation, which is really cool. And it looks like I don't have my calculator, but yeah, I'll use my phone calculator. I should have got it between videos, and I didn't, so that was silly of me. 65 times 9.81 multiplied by 122 divided by 265. Looks like 293.6 watts, not newtons, watts. Power is in watts. Fantastic. Hopefully that made sense. So let's do another one. A 1,000 kilogram car accelerates from rest to a velocity of 15 meters per second in 4 seconds. Calculate the power output of the car. And we're going to ignore friction. So we know the mass of the car is 1,000 kilograms. We know velocity final and velocity initial. Velocity initial is 0 meters per second. Final is not 0, it's 15 meters per second. And we know time is 4 seconds. So we're looking for power. Power is work over time. We could find the displacement and find the acceleration, and then we could do work is force times distance. But that's just going to be a lot of work for us to do. We could also think of, well, we can think of work as change in energy over time, and what energy is changing. Well, we've got a velocity, and we're changing velocity. So for changing velocity, we must be changing kinetic energy. So EK over time. And we know change in anything is EK final minus EK initial over time. This car starts from rest. So that means VI is 0. If VI is 0, that means the kinetic energy initial is 0. So that cancels out to be 0. And we're left with power is equal to kinetic energy final over time. And we know that that is 1/2 mv squared over time. And we can do 1/2 multiplied by 1,000 multiplied by 15 squared, all divided by 4. And that is going to be 28,125. Power is in watts. Hopefully that made sense. I think the hardest part sometimes of these problems is figuring out, you know that we're going to start with this formula here, but we don't necessarily know work, so we have to look at it in terms of force times distance or change in energy, and it's really dependent on the situation. So don't panic, take a breath, try a couple different things and see if it's working. One more useful formula, it only is for constant velocity. I don't necessarily always show it, but we know that constant velocity is displacement over time, constant velocity only, and we know power is work over time, which is force times distance over time. So only for constant velocity, you can see here that that's equal to V. So I can't say this enough, only for constant velocity, power is equal to force multiplied by velocity. Power is a scalar, by the way. I don't know if we mentioned that at the start. Cool, I think that's it. We will do some practice problems in class, and hopefully it starts to stick. Thank you for watching, and don't forget to like and subscribe.